First, I will start by reviewing the concept of a transaction and how transactions allows us to achieve ACID properties, and then focus the remaining of the session on concurrency control using two major ways of achieving concurrency. One is a lock-based concurrency control, and the other mechanism is optimistic concurrency control, particularly using multi-version concurrency control. So by the end of this session, hopefully you should really understand what concurrency control is in the context of a database and how we achieve it. What are the mechanisms to achieve concurrency control? So first of all, our goal when we build a database management system is to achieve these ACID properties, which we discussed before. ACID stands for atomicity, consistency, isolation, and durability. And to achieve these properties, the concept of a transaction comes in. It's an important abstraction, an important mechanism that the database gives us to help us achieve these ACID properties. So a transaction, as far as the database is concerned, a transaction is a sequence of read and writes. That's what a transaction is. And what we want this read and writes to act as a single unit. We put reads and writes together as single units, and we want them to all be successful, or if something happens in the middle, some kind of error happens in between these multiple operations, we want to undo the partial changes. The main thing is we don't want partial transactions. Partial transaction is very annoying and very undesirable. We all, at certain stage, experimented some kind of partial update. For example, we book a ticket, and then we receive our bank account was, let's say, debited, and we never received an email from the airline. It happened to me, I think, 2-3 weeks ago. Okay, I had to call the QNB. QNB says, oh, yes, we can see that there is a transaction which is on hold. So they have this on-hold mechanism. When I call Qatar Airways, they say they don't see my transaction. So the solution is that transfer or that payment will be on hold, I think for 3 weeks or so, and then it returns back to the account. So it is, of course, undesirable situation, and you need to do follow-up to make sure, because you need to make sure, so you want to see whether you want to do another booking or you wait for to receive a ticket. You are not sure. So this partial transaction or partial update, it's undesirable. And that's what highlight the need for the concept of a transaction. So a transaction, it can be defined, the transaction boundary, where the transaction starts, where it's finished, it can be decided by the developer. So as we saw last time, as a developer, I can explicitly start a transaction, and then inside it do multiple updates, inserts, and deletes, and all the operations between the start and commit are considered as one unit. Typically, the way we do it is I do here a try, and I'll do start transaction and put some SQL operations between the start and the commit. And typically, I'll do here a catch. If there is anything that went wrong within these statements, I will roll back. That's the typical programming style that most developers will do. So they will do try, begin the trans, do whatever operations that need to be considered as one unit, go ahead and commit. This is the happy day scenario. This is what we wish everything will go well. And this is the kind of the unhappy day path. If something goes wrong, I will just roll back. And we've seen this example last time. So to summarize in terms of definition of a transaction. So first of all, if you look in a very abstract way, database is nothing but set of named objects. These objects are usually tables. So they are named, and transaction comes along to read and write these objects. So a transaction at the end of the day is a sequence of read and writes of these database objects. And the outcome of transaction either commit, which means make all the changes that have been made by the operations within the transactions, make them all permanent and save them to the database in a durable way, or if something goes wrong, undo the operation that has already successfully completed, undo them, so that as if this transaction never existed. That is the idea of transaction. And it's very, very powerful because it simplifies our life as developers. Our life as developers, we can just focus on writing the normal flow, or the regular flow, or hoping that everything goes okay. And if something goes wrong, we shouldn't worry too much. We can just, in one statement, roll back, and database will take care of undoing the changes that we have done so far. That's the idea of the transaction. And transaction allows us to achieve these asset properties. And these asset properties, if you look at them carefully, you can think of them as correctness criteria. For a transaction to be correct, it needs to meet these 4 criteria. The first one is atomicity. All the operations, either all of them succeed, or if something goes wrong, we roll back, as if the transaction never existed. The other correctness criteria that the transaction needs to achieve, and this will be the focus of our discussion, is consistency. This is not our focus of discussion. The discussion will be focused on the isolation, which is achieved by concurrency control. Consistency here just means that the database is always kept consistent. Usually, this is the way it is achieved is through constraints. You can define some constraints on your database, and if these constraints are violated, your transaction will be rolled back. If you recall, in last week demo, I created in the accounts, in the bank account table, I created the constraints, which says the balance should never be less than 0, for example. So that is a constraint I defined. That constraint helped me to achieve to keep the transaction table, the accounts table consistent. So any transaction that violates that constraint that I defined will be rolled back. In fact, it will be automatically rolled back by the database, especially if it's one statement. What I mean by this, by the way, the transaction, every statement you run against database is implicitly included in a transaction. So if I try, let's say, to insert into, let's say, an account, although it is one statement or one operation, that operation is implicitly a transaction. So if that operation violates certain property or certain constraints, it will be rolled back. It will be aborted. Okay, the other correctness criteria is isolation. Isolation, this is where we will spend most of our session. This is that if a transaction is currently doing some changes to my database, those changes should not be visible to other transactions until that transaction commits. So that is very important. Otherwise, concurrently running transaction might end up with dirty reads, as I explained last time, and I will highlight this in more details as we move forward. So isolation, it gives the impression to concurrently running transactions, it gives them the impression that as if they are running alone, there are no other concurrent transactions. as they have the whole database to themselves. But in reality, there are concurrently running transactions, but without negatively affecting each other. And finally, after all this hard work, any committed transaction, we don't want to lose them. We want to keep them permanently persisted in our database. And this property is known as durability. So these are kind of our goals, what transaction properties we want to achieve. And these are the mechanisms in very high level. Of course, I will go through the details of some of these mechanisms. If we look at atomicity, for us to achieve atomicity, one of the mechanisms, the most widely used mechanism, is login. What I mean by login here, which I will explain further in the next part of this session. The login is any change I do to the database, I keep a log of the change. So for example, I have changed a particular row in a particular table. I need to record the old value and the new value. So every change, every insert, every update, before I make it to the actual data file, I keep a log of the change. And this log, this is what allows me to achieve atomicity. Because if I have a transaction, and if I want to roll it back, how can I roll it back? I basically go through the log and take the old values and put them back as they were before the transaction. So without login, I cannot achieve atomicity. So the mechanism used for achieving atomicity is by having a log. And a log allows me to revert back to the old state if I decide to abort the transaction. So the login is the most widely used mechanism, but there are other mechanisms such as shadow paging. Shadow paging means when I start a new transaction, any changes I want to do, I kind of put them in a separate page or in a separate copy. So if I want to do some change, I take the original copy, make the change. Sorry, I make a copy of the original data pages that I want to change, make a copy of them, make the changes in the copy, and if I manage to commit the transaction, then I reflect the changes in this copy on the actual global database or the actual database. So if I need to roll back, then I just throw away that shadow page or that copy page. That's the idea of shadow pages. But the most commonly used mechanism is logging. I make a record of every change. In the second half of this session, I will go through the details of how the logging works and how it helps us to achieve atomicity. Now, consistency is typically achieved by defining some integrity constraints in my database. For example, integrity constraints could be, as I explained, one example, I can put a rule if no transactions should ever put my balance of my account less than 0. That could be a constraint. Or let's say an order must have a customer. So I cannot insert an order without customer. Those are constraints you define in your database, and database will take care of making sure every transaction meets or kind of respects those constraints. If any transaction violates such constraint, that transaction has itself to blame, because that transaction will be rolled back. It will not be accepted. Okay. Now, isolation, for you to have this property of isolation, where you can have multiple concurrently running transactions, but they feel like, or you give them the illusion as if they are running by themselves. There is no concurrency. For you to achieve this, you need some kind of concurrency control protocol. or concurrency control mechanism, and that's what I'll be explaining in more details in this session. Those concurrency control mechanisms can be categorized in two major categories. There is pessimistic lock-in based mechanisms, and there are optimistic typically multi-version concurrency control mechanisms. I will explain them in much more details as I move forward. Okay, now for durability, which is if you start a transaction, you go through and you do the operation that you want, and then at the end you say commit, make this transaction, fully save it, make it permanent. Then database gives you 100% guarantee that your changes will not be lost. How can we achieve this durability and give guarantees to the user, to the database user, that the committed transactions, the effects or the changes made by the committed transactions are not lost? Is by, again, using login or shadow pages. So login that we discussed in the atomicity, if you remember when I want to update some data file or some page on the data file, I first need to bring it to the buffer pool. Yes? So this is true for any file. I cannot change the file directly on disk. I always bring it first to the data pool, to the buffer pool, and in the buffer pool, I start making my change. I start making my change to the page. Sorry, I start making my change. I start making my change to the page. Now, this page, for performance reason, if you recall, for performance reason, I don't just go ahead and once I finish with the page, I get rid of it and push the page back to disk. For performance reasons, I don't push it immediately to disk. I will push it later when I need more space or more memory space. But the problem is, if something, we know that memory is volatile. The buffer pool is in memory, and memory is volatile. If the server needs to restart, or it crashes, or the power goes off, then my buffer pool is lost, and the changes there are lost. And this is directly violating this guarantee that the transaction needs to achieve, which is durability. This is where the login comes to the rescue. So you remember the login? I make a log of all the changes that the transaction made. So when I say please go ahead and commit the transaction, what I'll do with the log, I'll take the log and push it to disk and say, yes, your transaction is committed. Although the changes are not reflected in the actual data file, but the changes are already captured in the log. So if the database for some reason needs to restart, no problem. When it restarts, it goes through the log and replay the committed transactions to bring the data file to a correct state. Yeah, that's basically the idea of a log. And I will explain it, of course. Yes, please.
What will happen if something happens to the log?
Yes, of course. If something happens to the log, then it's the data changes are lost permanently. Yes. So that's why the log is so critical that it needs to be taken care of very carefully. That's why if you remember the RAID that we discussed, so most likely you have to have some kind of mirroring to have multiple copies on multiple disks, and you might even replicate that log server to have a standby server in case the whole server goes away. So the log is so critical. If you lose the log, the changes that has been done since the last backup will be lost. So the log is very, very critical. You really need to be taken care of. So I will explain further, but this is just to give you the big picture of the mechanisms. So to summarize, atomicity is achieved through logging. As an alternative mechanism, you can use shadow paging. Same thing for durability. Durability is achieved through logs. The only thing here, the log needs to be pushed to disk before I declare that the transaction is successfully committed because of the durability, to be able to give this durability guarantee. Consistency is just, you need to define constraints. Database will take care of enforcing them and roll back any transaction that violate the constraints that you define. Isolation, you must use a concurrency control mechanism, either lock-in based mechanism that I will explain, or a multi-version concurrency control mechanism that I will also explain. So those are goals or guarantees, and those are the mechanisms used by the database to deliver them and to achieve them. Okay, so let's now zoom in and discuss more this concurrency control and how database achieves concurrent transactions without side effects, without undesirable side effects. So concurrency control, what it means is I want to have multiple concurrent transactions concurrently running. And these transactions may be reading and writing data items concurrently. So, and my goal is to achieve the maximum throughput and the minimum response time. Because I could have made life easier and just allow one transaction at a time, which is known as a serial schedule. Just queue the transaction and one at a time. I don't have any problem with concurrency. I only allow one at a time. But what is the price I will pay? Yes, the response time of the queries will be much higher, and the users need to wait longer to get their queries answered. And the system throughput will be low. Instead of processing, let's say, 1,000 transactions per second, it will be processing 10 transactions per second. So I don't want to go for serial execution or only one at a time or single threaded. I want to have concurrently running transaction, but at the same time, I don't want to sacrifice correctness. Yeah. So I don't want to have transactions interfering with each other and doing the wrong things. When I say the wrong things, there are three anomalies, three problems that can happen when you allow transactions to interleave, to have concurrent transactions. If you don't do anything about it, you will end up with one of these three anomalies or multiple of these anomalies. So let's try to understand these anomalies that we want to avoid and how we will avoid them. By using a concurrency control technique or mechanism or protocol to achieve this concurrency without sacrificing correctness. This is what we want to avoid. I will explain them in high level and then give you examples to illustrate those anomalies in a very clear way. So the first anomaly is a lost update. Transaction 1 comes along, does some change. Transaction 2 comes along again, change the same thing, and we end up with only the changes of transaction 2. Changes of transaction 1 are lost. I will show you an example to illustrate it. Dirty read, we did it last time together. Dirty read means transaction 1 comes along, it did some changes. Transaction 2 comes and read the changes that T1 has done. But T1 for some reason decided to roll back. And then T2, transaction 2, ended up with dirty read, which means some changes that has been rolled back. We don't want to end up in this situation of dirty read. The other one is unrepeatable read. Sometimes if you have some complex logic, you read one data item, you do some work, and then you come back and read that same data item. Ideally, those two reads should give you exact same result within the same transaction. If you don't do some, if you don't do something about it, which means you don't do some concurrency control, two reads in the same transaction might give you different results, and this is called unrepeatable reads. So these are three anomalies that concurrency control tries to avoid. The first is loss update, second is dirty reads, and third is unrepeatable reads. We want to avoid these three because these three will cause us incorrect and inconsistent database. So let's look at each of them through small illustrative example. Okay, so here is the example. So let's say Ali and Sarah, let's say they have a shared account with two cards. So any of them can go to an ATM and basically withdraw some money from their account. And let's say the initial balance of the account is $400. So Ali goes ahead and withdraw 100. So the logic the ATM will be doing, it will read the current balance. It will check, it will ask the user, give me how much you want to withdraw. It will check if the amount to withdraw is less than the balance. Then it will gives you the amount that you requested, and it will reduce that amount from the balance. That's basically the logic. So in this scenario, it will read 400. Ali asks for 100. 100 is less than 400. We allow this transaction. So the balance will be after Ali's transaction is 300. Okay. Now, Sarah's comes along and she wants to withdraw 50. 50 is less than 300. So we allow this 50 to go long. And the balance after Sarah's withdrawal will be 250. Yeah. So that in a consistent database, let's say if they don't do it concurrently, this should be the state, the database state, or the balance after the two withdrawals go ahead. Now, if they happen at the same time, then some lost update might take place. So let me illustrate this. So in here, there is no, they do it in a non-concurrent way. One of them did it at, let's say, 5 p.m. The second person did it at 5:05. No problem. There is no concurrency. The expected results will be equal to the actual result, which is 250. Now, take a look at this if they do it exactly the same time, concurrently. So what happened is, this is Ali's transaction, T1, and this is Sarah's transaction, T2. Okay, so Ali reads the balance, which is currently 400, which is currently 400. Meantime, Sarah's was so quick. She really needs that 50 riyal or $50 super quickly. It's super quick. Basically read the 400. She asked for 50. So 50 is less than 400. No problem. We will allow this withdrawal to take place. And quickly updated the balance and wrote the balance back to the database, which is basically what we have here. The current database says 350. But Ali is still thinking that the balance is 400. So they went ahead and say, okay, give me 100. System will say, no problem, 100 is, you have enough balance to cover 100. We'll take the balance that we read at the start of the transaction, deduct 100, and this is the new balance, and we go ahead and write it. So what happened here? The change of this transaction went ahead and overwritten the change of T2. So T1 overrode the change of T. sorry, T1 overrode the change of T2. Okay, and this is a lost update scenario. And who is losing? Who is this crying guy? Of course, the bank. Yeah. So the balance here is supposed to be 250, and the balance now is 300. This is the lost update scenario.
But also, this can be considered as anti-reader.
No, not really. Dirty read is in the case T2 comes along and reads some data that T1 has changed, and T1 decided to roll back. So T2 will have at hand the dirty data. We don't have a dirty.
Also is dirty because it is changed.
No, it's not really dirty. It's basically not what we have here. What we have here is that this guy has come along and read this data. Meanwhile, somebody else wants and change the state of the database. It's not really dirty because those terms are very, very precise semantics. Dirty read means you read something that was aborted. That's what dirty read here means. Here it's a lost update scenario. Lost update, I read something. Before I made my changes and saved them back to the database, somebody else came along and changed what I have read. So when my change makes it to the database, the change that was made while I was still in the process of changing that particular data item, that change that came along will be lost because my transaction will overwrite it. So this is basically a lost update scenario. Okay. So there's another scenario which is quite similar, but this time Ali was quick. So in here, with this read the balance, which is 400, went ahead and asked for 100, so the new balance is 300, quickly made the withdrawal and saved the new balance to the database. While Sarah is still kind of thinking about it and working on it, meanwhile, the 400, she's still using the 400 that she read at the start of the transaction. But this 400 is no longer the true value. That value the balance has now changed by Ali's transaction. So here is our T1. T1 this time was faster to go ahead and commit the change, while T2 is still thinking. So in this scenario, Sarah's withdraw 50, so the new balance is 350 because she read 400 at the start of the transaction. And now you can see the bank is even crying more because we have even the impact of this lost update is even greater. Yeah. So the balance is supposed to be 250 and now it's 350. So there's a lost update. Same problem. T2 read some data while there was another transaction that came along and changed that data in the database. And this T2, when it's time for it to commit its changes, it's overwritten the change that has been done by T1. So this is called the lost update scenario. This is very undesirable, as you can see. We have some inconsistent states that we want to avoid. And you will see shortly very simple mechanism we can use to avoid this lost update. This is the dirty read that we've seen before. So the dirty read, here is a T1 came along, read A, and changed it from 10 to 12. And then another T2 came, concurrent transaction came, and read A after T1 wrote it. But T1, for some reason, decided to abort. Then, basically, T2 now has a dirty read. The reality in the database, what is the value of A in the database? It's still 10. It did not change to 12. Why it did not change to 12? Because T1 aborts. This is a scenario of a dirty read. Dirty read, when a transaction comes along read some data from another transaction changed, but the other transaction decided to abort. Then this T2 will end up with the dirty read. Okay. The other scenario is unrepeatable read. Unrepeatable read. In this scenario, what we have is we have a transaction T1. It reads E. It went ahead, does some other work, and kept itself busy. And at a certain stage, it came back and tried to read A again. And unfortunately, you can see here the value of the first read is different than the value of the second read. Why? Because meantime, while this T1 was going along, doing its work, some other transaction came along and changed A. Yeah? So this scenario, we have unrepeatable read anomaly. So if we allow concurrent updates without doing anything about it, without implementing a concurrency control mechanism in place, then we might end up with one of these, or one or multiple of these anomalies. 3 anomalies, which are lost updates, dirty read, and repeatable read. Yes, please.
Unrepeatable reads is positive, right? Or negative?
No, a repeatable read is...
I mean, is it positive? Because the lost update and the second one is negative. It will broke the database. But here it's okay, right?
No, it's not okay. But if, for example, let me give you a small scenario. So, for example, I went ahead and let's say, go to employee table, and I read all the employees and give them 10% increment. Okay. So now, if I read again in my transaction, I should get the salary equal the salary at the beginning times 1.1. Yes? But some other transaction came along and changed the data while I was doing some other things. And I was expecting the salary after the increase will be the previous salary times 1.1. And now I find it different because some other transaction came along and did some update. So my results is inconsistent. My transaction will be so confused. What's happening? I just changed the salaries. Maybe I changed by 10%, and I find after I do a second read, I find it changed by 20%. How come? Because some other transaction came along and did some change.
But
so
it's likely it should be $20 plus percentage.
No, what I mean here. Here I read some value was 10. I expect this value to be the same if I read it again and again in the same transaction. For some reason, that's my requirements in this transaction. I want a repeatable read. Not all. This problem only occurs if your transaction reads the same item multiple times, the same data item multiple times. It is logical to expect it to be the same. But suddenly, you start seeing different values. It's very confusing, and you cannot build like some good reasoning or some good algorithm, something reasonable on some values that keep changing. Yeah, you want some values that you can read them again and again, and always the same. They should not change within the same transaction. If this is a requirement for you, then you need to do something about it to achieve that. Otherwise, if you just let concurrency go by itself without doing any concurrency control mechanism, you will end up with this undesirable and repeatable read. Are you following? What this means is, you say, okay, no problem, I want concurrency. I just let the transaction do whatever they please. If you do this without concurrency control mechanism, you will end up with these 3 problems. There is no doubt you will end up with them. Okay? So can we just raise our white flag and say, khalas, we can't do anything about it? If we want the concurrency, this is the 3 prices we will pay? No. There are mechanisms to achieve concurrency, which gives us higher throughput, better response time. At the same time, preserve correctness. But we have to put some smart mechanisms in place in the database. Is clear? That is I'm just trying to motivate the need for such mechanisms. If you don't put them in place and you just let concurrency go ahead, you will end up with these three problems. We want to avoid them. Yeah? Okay. Now, before we go into the correct, before we go into the actual mechanisms, I don't want to spend too much time on the theoretical aspect, but this is very important to really understand. So this correctness, this concept of correctness, of having a concurrent transaction but still keeping correctness, people have spent some time defining what we mean by correctness in this context when we talk about concurrency and preserving correctness. So this preserving correctness in the literature, people studied this problem, and it is known as conflict serializable schedule. You need to create a conflict serializable schedule. What I mean by this, first of all, let's define what is a schedule. What is a schedule? Is basically the order in which the database, the transaction operation will be executed. That is known as a schedule. So at the end of the day, what we can do, this is our ideal schedule. What is an ideal schedule? Is a serial schedule, which basically every transaction will run by itself without any other concurrent transaction. This is the ideal. Yes? So every serial schedule is a correct schedule. Why is it correct? Because there are no concurrent transactions. Yes? Okay. So our concurrency control mechanism, at the end of the day, the goal of a concurrency control mechanism is to create a schedule, that is equivalent to a serial schedule. What does that mean? That if I run this serializable schedule, I get exact same result as if I have a serial schedule. Okay, let me put it another way. So if we want to put this concurrency problem we just discussed, if we want to get rid of them 100%, what is the best solution to get rid of them? Serial schedule. Okay, so serial schedule is kind of a goal, or kind of the best solution. So concurrency control tries to create a schedule that we call, what is the name of this schedule? Serializable. Another name for it is conflict serializable. Yeah? What is the idea of this conflict serializable schedule? It is equivalent to a serial schedule. What does it mean, equivalent to a serial schedule? It has the same results. You get exactly the same result as a serial schedule. Yes? Now, and then people start saying, okay, how can I verify that a schedule is serializable? Are you following? How can I verify that a schedule is serializable? So serializable is a property that you can verify. Yes, a property that you can verify. So people invented this very nice mechanism to verify that schedule is serializable or not serializable. What do we mean by a serializable schedule? It's a schedule that is equivalent to serial schedule, which means if you run it, although it allows interleaving and it allows concurrency, it will still give you exact same result as a serial schedule with the extra benefit of higher throughput and better response time. That's what we want at the end of the day? Yes? Okay. So, yes, please. What is a serial schedule? No concurrent transactions. It doesn't allow concurrency. One after the other. T1 finish, then T2 start. T2 starts, finish, then T3 starts. Okay. Okay, so let's take a look at this and then I'll come back. All right. Here is a schedule. Here is a schedule. And I will explain it nicely here. So here I have three concurrent transactions. Can you see them? T1, T2, and T3. Some of them are reading and writing and so on. So I want to verify that this schedule you see in front of you, whether it's serializable or not serializable. Okay? So one way to do it is to build what is known as this dependency graph or precedence graph. That's another name for it. Dependency graph or a precedence graph. Okay, so the way I do it, I'll just create a graph. What are the nodes of this graph? The transactions themselves. This is T1, T2, and T3. And what are the nodes of this graph? The nodes of this graph, what I'll do here, I look at a reading A, and I'll find if there are any subsequent operations that are conflicting with this operation. So first, let me explain what I mean by conflicting. Is a read conflicting? If I read and somebody reads the same thing, is it a problem? This is not a problem. If I read and somebody writes, is this a problem? It is a problem, yes? Because if I read and somebody writes at the same time, yes, I will end up with lost update. Because I read something, somebody went along and changed it. When it's my time to change it, I will override the change of that concurrent transaction. So this one, no, it's conflicting. What about a write? Of course it is conflicting. So these are the type of conflicts that we don't want to have. Read-write conflicts, write-read conflicts. If I write something, if somebody reads it, they are running the risk of getting a dirty read because I might change my mind and abort. So this one is also undesirable. The only thing that is okay, read. We are talking about the same item. If you are reading A and I'm reading Z, there is no problem. Here we're talking, you are reading A, I am reading A. I am reading A, you are writing A. If we are talking about the same thing, then we don't want this. If we have this read followed by write, it might cause conflict. Write followed by read, it might cause conflict. Write followed by write, it might cause a conflict. Yes? Okay, so back to this example. My goal is to decide whether this schedule you see here is serializable or not. How do I make a decision about this? By creating a dependency graph. How do I build this dependency graph? Create nodes for each transaction. And then look for each transaction, take a look at this transaction and say, this is a read A. In T2, is there any conflicting operation with this read A? No, no problem. This read A, is there any conflicting transaction in T3? Yes, you can see here, this one is conflicting with this. Yes, so once it is conflicting, what I will do, from T1, I create a node. So I create an arc or an edge. I create an edge. If I want, I can label it if I wish. A. So there is a conflict here. Yes. That T3 is doing something conflicting with T1. Clear? Okay. Write A. Can you see it here? Is there anything conflicting with write A here? No. With T3, is this something conflicting? Yes, but I already have a node, an edge for it. Yes? Now in here, read B. Anything coming after it and conflicting with it? Okay. So after it, read A. There's nothing coming after it and conflicting with it. Write B. Anything after it and conflicting with it? No. No problem. Okay. Read B. No, sorry. In here, let me just see. T1. Yes, yes. Okay. T2 here. Anything with this one, here it is. Anything with this coming after it and conflicting with it? T1. You can see here, yes? This one is reading, this one is writing. So I will create another node here. I can label it if I wish B. So definitely there is a conflict in here. Okay. Anything with T3? There's no conflict with T3. What about this write B? Anything coming after it and conflicting with it? T1. Already I have an edge on this. What about T3? T2 and T3, any conflicts? No conflict. Now, once I finish this dependency graph, can you see it here? This dependency graph, what it indicates to me, that this schedule is a serializable schedule. Why did I make this conclusion? Because this graph does not have a cycle. Because it does not have a cycle, this is a serializable schedule. As long as the database does T2 first, let T2 finish and go ahead, followed by T1, followed by T3, we will be fine. And this one will be a serializable schedule. It will be as if I let T2 finish completely by itself, and then let T1 come along and do its work completely by itself, as if I did a serial schedule. So this is to highlight. Of course, database don't worry. Database will not do this. This is just kind of somewhat to a certain extent an academic exercise, just to let you know that there are serializable schedules out there that are equivalent to a serial schedule, and you can prove it. That's the point in here. But database does a much simpler way to achieve serializable schedule without doing this dependency graph. Because the problem with this dependency graph, to build it, you need the knowledge of all the operations of all concurrent transactions. We cannot wait until we get the full knowledge what each transaction will be doing. Yeah, but ideally, this is very important because we are looking at the end of the day, concurrency control. What is the role of concurrency control? Is to produce a serializable schedule. What do we mean by serializable schedule? A serializable schedule will have the same results as a serial schedule, with the extra benefit, of course, of concurrency. Yeah. Okay. So this is there is a conflict serializable schedule, which is T2, T1, and T3. This is in this order. If we do it in this, if the database allows the transaction T2 to commit first, followed by T1, followed by T3, we will have none of those problems that we just discussed. Yeah, and notice here, although T3 started later than T1, but it should go first. Sorry, T2 here. Although T2 started late, it should go first. Otherwise, we will have conflict. Yeah. Okay. So let me show you another example. Here is another example. Let's just build. Although we have it here, let me remove it, and let's build a dependency graph for this schedule. This is a schedule. Okay. So how do we build this dependency graph? First, I create nodes that represent the transactions. Okay. So T1, T2, and T3. So I will start with the transactions of T1 and see if there is any subsequent operations in other transactions that conflicts with this operation. So T1 reads A. Is there anything that came after and conflicting with it in T2? Yes. Can you see it here? So I draw a node. Sorry, I draw an edge between these two nodes. I can label it if I wish, just for me to, okay? So there is definitely a dependency between T1 and T2 when it comes to reading and writing A. What about with T3? Yes, same thing. Okay. Now, here I'm writing A. Anything coming after A, after writing A and conflicting with it? In T3, but I already have an edge already for this. So T1 is done. Okay. Now T2. Can you see it? Is there any operation that came after the writing A and conflicting with it in T1? There's one in T3 and one in T1. So there is T2 and T1. Can you see it? There's dependency here. And between T2 and T3. Now T3, is there anything come after it and conflicting with it? No. This is my dependency graph. Is this a serializable schedule? No, this is not a serializable schedule. Why? Because it has a cycle, because it is acyclic. So this is not a serializable schedule. If the database goes ahead and execute this schedule, it will end up with one of these anomalies we discussed. This is not a serializable schedule. Okay? So, and I gave you so many examples just to kind of practice. All right. So this one will end up in a lost update. So for example, let's say, you see here, between T1 and T2, there will be a lost update. Can you see it? T1 read, this is same as what happened to Ahmed and Sarah. See here, T1 read A. Meantime, before it made its changes, T2 came along and writes A. Halas. Now, if T1 comes along and writes A, what will happen to the change made by T2? It will be lost update. So is this a serializable schedule? No, because it will create an anomaly. How do we know? By creating a dependency graph. If it has a cycle, then this is not serializable, which means it's not equivalent to any serial schedule. This cannot execute. Yeah? But luckily, as I show you shortly, database does not do this. Why? Because this assumes you need to have knowledge of all the operation each transaction is doing for you to build this dependency graph. Database does much simpler and much smarter way to achieve exact same thing, but in a much, much simpler way that I will explain shortly. Okay, so this is the recap just for the fundamental concept of concurrency, the fundamental concept. So concurrency control, why do we need it? Because if we go with one transaction at a time, our performance will suffer. The throughput will be low, the response time will be high. We don't want this. We want concurrence. We want to allow transactions to run concurrently, but without paying the price of the incorrectness introduced by the three anomalies: the lost update, the dirty reads, and the unrepeatable reads. Okay, so for us to achieve this, we must have a concurrency control mechanism. At the end of the day, what is the role? What's the mission of this concurrency control mechanism? Is to produce a serializable schedule. What do we mean by a serializable schedule? It's a schedule that is equivalent to a serial schedule. What do I mean by a serial schedule? It's a schedule that does not allow concurrency. Yeah, that is the idea. Okay. Now, dependency graph is something, just kind of an academic exercise to prove to you, by the way, there are out there serializable schedule, and you can know whether they are serializable or not serializable. Okay. Now, let us now move on and see in practice what databases do to achieve a serializable schedule. Okay, so database, they do two major techniques to achieve concurrency, two major techniques for concurrency control. We call them concurrency control protocols or mechanisms. These two categories can be as follows. So we have pessimistic concurrency control protocols and we have optimistic concurrency control protocol. So pessimistic here, they assume the worst. They assume that conflicts will happen, that anomalies will happen, and this pessimistic concurrency control, they try to avoid them in the first place. I'm not even going to go to that danger zone. I will just not allow it in the first place. That's what pessimistic concurrency means. And what they use for this, they use lock and change the current database state. So they take the database state. Before you do any change, before you can change something, you lock it, and then you make the change. So it's a lock-in based mechanism that I will explain in more details. The other family of technique, they call themselves optimistic. Optimistic here, they say, okay, the conflicts and the anomalies are the exception, not the rule. So let's not try to avoid them. Let's go ahead with assuming that they won't be conflicts. And if the conflicts happen, we will deal with them. It's a very different approach. In here, they don't allow conflicts in the first place. In here, they tolerate conflicts and anomalies, and if they we go ahead and try to discover those anomalies, and then undo them or do something about it. Yeah. So here, the most common and the most widely used mechanism to achieve this, it's called multi-version concurrency control. Maybe many of you in your review papers, you might have come across this. Okay, I will explain both of them. So the idea of this multi-version concurrency control, instead of going and changing in place, changing the current state of the database, the transaction will never directly change the database directly. What the idea here is each transaction will have its own workspace, private workspace, and it does the work in this own workspace, private workspace. It's kind of working on a separate copy. Each transaction has its own copy of the pages that it will change. It will go ahead and do whatever changes it needs to do. And guess what? Before those changes are committed and made available in the global database or in on the common database, what we will do before we reflect those changes in the private copies in the global copy, we verify that those changes do not conflict with other changes. Yeah? If there is conflict, what will happen to your changes? We throw them away. We say to you, sorry, we have to abort because you are conflicting with some other concurrently running transaction. You see here is a very different mechanism, achieving the same thing, but different, very, very different way. Lock-in based and multi-version control based, concurrency control based. So let's go through each one and give a little bit more details. Okay, so first of all, lock-in is very, very popular mechanism for achieving concurrency control. And the idea here in the database, we have a very important component called the lock manager. It's a component called the lock manager. When a transaction comes along and say, I want to read this particular data item, or I want to write to this particular data item, what the transaction should do first? Request a log from the log manager. Yeah? The log manager will say, oh, you want to access A. Do you want to access it for read or write? Say, I want to access it for write. Sorry, for read. I want to access for read. The log manager will say, oh, I have some other transactions reading the same data item. Is a read okay or not okay? It's okay. So this is called a shared lock. No problem. The lock manager will hand you over shared lock, and you can enjoy reading that particular data item. And then suddenly you say, I want to upgrade that shared lock, which is allowing me to read. I want now to write. You go back to the lock manager and say, please give me the right lock to this data item. The lock manager will look up its locking table and say, sorry, this data item you are requesting to write is locked by other transactions. What will happen to the transaction asking for that lock?
Wait.
It must wait. That's it. It must wait until when? Until the lock is released. Once the lock is released, we wake up that transaction waiting in the queue, say, okay, now the lock is yours, go ahead and make use of it. It's very, very simple mechanism. So let me show you this visually. Here it is. So what I have here, this is two transactions. And what I have is T1 and T2. So T1 wants to read A. Before it reads it, what it should do? Go to the lock manager and say, please grant me a lock on this data item A. What type of lock it will request? Shared lock, because you just want to read. Yes? Now, being the first transaction, nobody is using that particular data item, the lock manager will say, here you are. This is the lock. Do whatever you want to do with it. Okay? And then suddenly, let me see. Yes. In here, no. In here, what it's trying to do, maybe in here, this is very, very sneaky transaction. It asks for a write lock or an exclusive lock directly. Just let's assume this. So it's asking for an exclusive lock on this particular item, on item A. The lock manager will grant it the exclusive lock, and then T2 comes along and say, please give me a lock on A. I want to read it. What the lock manager will say? Denied, you must wait. Yes, we must wait. Then T1 will come along and read A and write to A, and it can read A again because it has the lock. It can do whatever it pleases with it. Once it's done, I'm done with this item A from the database. I unlock it, which means the lock is now released, and it's given to transaction T2. Transaction T2 will get the lock, will read, write, and unlock and commit. So this, if we write a dependency graph for this schedule, you will be surprised it is a serializable schedule. So locking, by this simple locking mechanism, the locking mechanism allows us to produce serializable schedule. By simply, here is how it works. So transactions request a lock from the lock manager before reading or writing a particular data item. The lock manager grants the requested lock if and only if it's not currently held by other transactions. If otherwise, the transaction that is requesting the lock will have to block and wait for the lock to be available. So once the transactions are done with the lock, they release them, and the lock manager can grant them to other transactions. And the lock manager always maintains an internal lock table to know which items are locked and by whom. So this way it manages granting locks. So you can already see this is the state diagram of a lock. State diagram. These are the possible states a particular data item can be at. So what we have here, we have a transaction requesting access to a particular item. For it to be to be granted access to this item, it needs to get a lock. Okay, so if the lock is available, it will be granted, and this will give the transaction an immediate access to the data item. Okay, if the lock is not available, the requester will go into a queue and wait for the lock to become available. Once the lock becomes available, the transaction can grab it and get access to the data item. That's basically the idea. Okay, so transaction is either enjoying the lock and making use of the data item, or it's waiting for the lock to be released. Yes, yes, please. Yes, this is the general idea. I'm getting to that. I'm getting to that one. So in general, the first idea is that whenever you want to read and write, you request a lock. If it's available, it will be granted to you. Otherwise, you wait as a transaction. You wait until the locks become available. Now, in terms of, yes, please.
This also will affect the response time and the throughput because the other transactions will wait. So
Yes.
we will not have like high throughput.
No, we will have high throughputs because basically there is a trade-off, as we discussed. If we just let transaction go without mechanism like lock-in, we will end up with anomalies. So definitely, yes, you're right. It will reduce our throughput, but not to the extent it is as if it is a serial schedule. So basically in here, we want a serializable schedule that is balancing the need for concurrency to improve throughput and performance while not paying the price of getting anomalies, while preserving correctness. So definitely lock-in will reduce our concurrency, and will reduce our throughput, will reduce our response, will increase our response time, but at the same time it will preserve correctness. So there is a trade-off that we need to balance. Yeah. Okay, so in terms of types of lock, there are two types of locks. There is a shared lock. We can use it for reading. Because the read-read operations are not conflicting, we can grant the shared lock to multiple transactions. There is no problem. And the shared lock blocks write access. So if any of the transactions have a shared lock, no other transaction can get an exclusive lock. Yeah. So the exclusive lock is only available when no other transaction is holding a shared lock on that particular data item. While the exclusive lock is used for write. So if a transaction wants to write something, to write to a data item, it must ask for an exclusive lock. And as the name suggests, only one transaction can have it, and it's not compatible with any other lock. You cannot have a shared lock with an exclusive lock or exclusive with exclusive. Exclusive means only one transaction at a time has that particular lock. Okay, so the read lock is always available, except if that item is exclusively locked. So if it is only shared, if we have it as a shared lock, we can give it to other transactions, no problem. When it becomes unavailable, only when a particular transaction manages to get exclusive lock, then the shared lock will be unavailable until that particular transaction finish and releases the lock. Yeah. Okay. For the write lock, so the write lock, it could be available once transaction managed to get it, it becomes immediately not available to any other transaction until such time the transaction that is having the exclusive lock releases it, and then other transactions can grab it. So this is, to summarize, shared lock, multiple transactions can have it. Exclusive lock, only one transaction at a time. And the exclusive lock is only available when no other transaction have shared or exclusive lock on that particular item. So this summarizes the relationship between a read lock and a write lock. So if a first transaction has a read lock or a shared lock, basically, that's another name for it, and the second transaction comes along and say, please give me a read lock on that same item, will the lock manager give it? Yes, no problem. Now, if a transaction has a read lock and another transaction comes along and say, please give me a write lock, you cannot have. A write lock and somebody asks for read lock, no. A write lock and somebody asks for write lock, no. So the only one that can be shared by multiple transactions is the read lock. The others are not. In the other scenarios, the other transaction will have to wait until the lock is released. Okay. Now, the lock-in by itself is not enough to produce fully serializable schedule. The lock-in by itself is not enough. You need, beside the lock-in, you need a protocol for locking. You need a particular way transactions should lock and unlock. And this protocol, very famous protocol, is called the two-phase locking protocol. And most databases implement this protocol. And what this protocol says, the protocol has two phases. A growing phase, a transaction has a growing phase and shrinking phase. Growing phase, transaction can ask for locks and get more and more locks. As soon as the transaction releases one lock, it can no longer get another lock. That's it. It needs to release the remaining locks. That's what two-phase protocol means. So in the two-phase protocol, what we have is, this is a particular transaction lifetime. It can ask for locks, no problem. It will be granted locks, granted locks. As soon as it starts releasing locks, the first one it releases, it cannot ask for more locks. If it asks for more locks, what the lock manager will say? Sorry, I cannot grant you. So this is a two-phase locking protocol. So just the locking by itself is not enough. So database implements locking with this protocol known as two-phase locking protocol. But this two-phase locking protocol by itself is not enough. It can create these two problems. It can create cascading aborts and deadlocks, and I'll explain each of them. So cascading aborts, what it means here, take a look at this. So what I have here, this is T1. It has an exclusive lock on A, an exclusive lock on B. Yes, so it's a read E and a write A, and then it starts unlocking. Can you see here? It's unlock A. Once it says unlock, it cannot ask for more locks. That's it. It's too late. It should now start releasing the other locks. The problem here, take a look at this. Because this one is now unlocked, can you see it? A is unlocked. Transaction 2 can come along and ask for a lock. Yes? And the lock will be granted on A because A is now available. Now, if T2 decides to abort, what T1 will end up with? Dirty read. So this two-phase locking does not protect you from dirty reads. What happened here, if we abort T1, the database will automatically also abort this one. So basically, the two-phase locking has this problem of cascading aborts because it allows a dirty read. The system will detect this scenario, and basically, if this one aborts, because there is a dependency between these two, this one must be also rolled back. So to fix this problem, if this problem is is causing this cascading aborts. There is another protocol more strict than this. It's called the strict two-phase protocol. What do you think this strict two-phase protocol means? What is the cause of this? Is that I am unlocking items or unlocking database items within the transaction. I have not committed yet. If just before committing, you unlock all at one go, then this problem will not happen. So this problem of aborted cascading aborts can be solved by using a strict two-phase locking. What is a strict two-phase locking? You hold on the locks until the commit time. Then you release all the locks at the end of the transaction. Of course, what is the price you pay here? Reduced concurrency, of course. There's a trade-off. You can already see here. There's a trade-off between correctness and concurrency. If you want to avoid this scenario of cascading aborts, you need to use strict two-phase locking. Now, us as developers, how do we control this? How can we control to tell the database whether to use strict two-phase locking or just two-phase locking?
Depending on the number of locks.
No, not really. But by the way, we cannot lock something explicitly ourselves. The database will do that automatically. We only, when we write our queries and our updates and inserts, there is no way you can kind of directly lock things. Yeah. But basically, you can control whether the database should use two-phase locking or a strict two-phase locking by using the isolation levels, transaction isolation levels. We kind of touched upon them last time when we introduced the topic, and I will go through them again. So the isolation level in a database, there are multiple levels. How strict you want and how much protection you want from concurrently running transactions. How much protection you want, you set the isolation level. There are 4 standard isolation levels that I will go through here. Yeah? By default, is it just two-phase locking? If you want to go higher, you can raise the isolation level further. So us as developer, we can set the isolation level we want as developers. And I will explain this shortly in a practical way. Yeah. So to summarize, our goal of concurrency control is to produce serializable schedules. What do we mean by serializable schedule? It is equivalent to a serial schedule. The end result is exactly the same as if you put these transactions one after the other, enjoying the whole database to themselves. Okay? Now, how do we achieve these serializable schedules? By using locking. Okay? We have a lock manager, and this lock manager manages granting and denying locks. Any transaction wanting to read, it must ask for shared lock on that particular item it wants to read. If it wants to write, it must ask for exclusive lock on the item. And the lock manager will make a decision. If it is shared lock, if other transactions are using it, no problem, you will be granted. If you are asking for exclusive lock and other transactions already have a lock on that particular item, that you have to wait. Now, just the locking by itself is not enough to achieve serializability, serializable schedules. You must also have, the lock manager must also implement the two-phase locking protocol. And what the two-phase locking protocol says? As a transaction, you can ask for as many locks as you wish. You keep asking for locks. Once you start releasing locks, you release the first one, You can no longer ask for locks. You have to release the remaining and commit or abort or do whatever you wish. But you cannot keep asking for locks and then you release and then ask. No. Ask as many locks as you wish, and then you go into the shrink phase. Even with this two-phase locking, it does not protect you from two problems. What are these two problems? Cascading aborts, which means even with this two-phase lock-in, you might end up with a dirty read scenario, but that dirty read can be avoided, but if you abort, the transaction that had a dirty read will also be aborted. So your abort will cascade to other transactions. If you don't want to end up in this scenario, what should you do? Raise the isolation level to strict two-phase lock-in. What strict two-phase lock-in means? Hold on onto your locks until just before you commit, then you release them. This way you don't give the chance to anyone to come in and end up with some dirty read. Yes? Okay. The other unavoidable problem is the deadlock. What does deadlock means? So,
The transaction keeps the lock for a long time.
that can exacerbate or can increase the chances of deadlock, but that's not a deadlock.
Deadlock, you're asking for something that's already locked.
Okay.
The transaction asking for the same lock.
So basically, the deadlock is T1 is waiting for T2 to release the lock, and T2 is waiting for T1 to release the lock. So they are waiting for each other, and it's a deadlock. They are waiting for each other forever. So how the database solves this? Sorry? Not both. It takes one of them. One they call it a victim transaction, and they abort it. So this is the most databases what they do. They have some kind of a background process running, and every few seconds or whatever it's configurable, this deadlock detection mechanism will run. Say, oh, I detected that these two transactions are not moving any forward. Choose one to abort, and then let the other one continue. Yeah. So let me show you what this means. So in the deadlock, this is the deadlock. So what I have here, so T1 has an exclusive lock on A, and T2 has an exclusive lock and shared lock on B. And now T2 is asking for a lock on A. It cannot get it because T1 has an exclusive lock on it. So it's waiting. And then T1 comes along and say, oh, please give me an exclusive lock on B. And now we have a deadlock. T1 is waiting for T2 and T2 is waiting for T1. And you can see here both are waiting. This is a message coming from SQL Server. I just didn't have time to show you. It's very, very easy to produce deadlocks. So basically, in the background, the database is running process. It will detect this. It might use precedence graph or whatever it might need to use, because in here you can use precedence graph because the operations are known. We know the operations each one did. So we can use a precedence graph and we can see a cycle. We will see a cycle in the precedence graph and we can detect this very easily. And then the database will pick up one of the transactions and basically abort it. And it will throw an exception to the caller. So your application in Java or .NET or Python will get an exception. And this exception will say something like this. This is the code, the error code. And it will say transaction process ID, whatever, was deadlocked on locked resources with another process and has been chosen as the deadlock victim. Rerun the transaction. I still remember this has been surfaced for end users, and suddenly they see this strange message at 8 a.m. and they freak out. And basically call in the help desk. I have been a victim of a deadlock. And so you need to be careful here. You need to absorb as developer, absorb this, I basically give a more friendlier message and giving choice to users what need to be done. So you might ask them, do you want me to try again? Do you want me to reload the form? Do you want me to reload the form and merge your changes with the current state? It's because in here, many things could happen. Because the other transaction might have changed what the user have asked you to update. So you can give the choice to user in more friendly way. But this is detectable. I mean, it will have, depending on which database we're talking about, it will have its own error message code, and you can have an exception, a proper exception handling in your application to either like automatically resubmit the transaction and you don't care, or you can ask the user to make that decision. Is clear? Now, database depend. There is no clear algorithm or a win solution for how to choose the victim transaction. It depends. Each database does it in a different way. You could choose, for example, the newest or the oldest, the transaction that started recently with the hope that it didn't do much. We can just abort it. Or we can choose the older one, because the older one may be locking so many things. If we abort it, we can help so many other transactions. So, you know, you can take a different reasoning. There is no winner here. By progress, which one, the one that did the least work, we can abort it. Or the one that did more queries. But the one that did more queries, maybe it has more locks with other transactions. And so on. So the database will choose one. We don't have a lot of control as developer. We'll choose one and basically kill it to allow the transactions to proceed further. Okay. Now what we have here is, so let me just summarize quickly before I move any further. So concurrency is something desirable. We want our database to be able to run transactions concurrently. Why do we want this to be built in our databases? To improve throughput, to reduce the response time, and at the same time, we don't want to pay the price of incorrectness. We don't want to end up with one or multiple of these anomalies, the lost updates, the unrepeatable read, and the dirty reads. So that's why we need to have concurrency control in place. One famous concurrency control mechanism is a locking-based mechanism. Before you read or write, you must get a lock. And you must get it according to a particular protocol, which is the two-phase locking protocol. And even this two-phase locking protocol still has issues. It does not protect you from two problems. One is cascading aborts. And that can be solved by sacrificing a little bit more of concurrency by doing strict two-phase locking, which means transaction will hold on their locks until just before the transaction is committed, then they release them all in one go. The deadlock, the other problem that still two-phase locking does not address is the deadlock. You might end up with deadlock, and the most common solution is database will have some background process detecting such a deadlock situation and aborting one of the transactions to let the system move forward. That's basically the idea of locking. And this locking with two-phase locking protocol achieves serializable schedule, which means it gives you schedules equivalent to a serial schedule. That is the idea. Now, the isolation is not a kind of a button on or off. It's a dial. You can set the level you wish. Yeah. So that's what is known as transaction isolation levels. So databases allow you to decide what is the isolation you desire, depending on your application. And this level defines what data your transaction is allowed to see. So these are the default four transaction levels, or four isolation levels, going from high to low. The highest isolation level you can achieve is serializable isolation level. You go to your database, before you start running your queries and your updates, you say set transaction isolation level serializable. What this gives you, it gives you protection from all this. You will get no phantom reads. I will explain what they mean. All your reads will be repeatable. If you read at the beginning of the transaction and start doing a lot of things and then read again, you are guaranteed to have exact same results, no matter how many reads you do in the transaction. Okay? And you will never get any dirty read. That is the highest level of isolation. When I say the highest level of isolation, what does that mean? The lowest concurrency you can get. And guess what? What do you think this serializable is doing? It's doing all the strict things. Strict two-phase locking, stinginess, keeping the locks until the last minute, acquiring all the locks in the beginning, yeah, and so on. So it's doing some very kind of aggressive locking. Now the other one is repeatable reads. Repeatable reads. Sorry, there is a little bit of... Okay. Now, repeatable reads, it gives you all the protections except you are not protected from phantom reads. That I will explain. Read committed, this is the most common and this is the most by default. In most databases, this is the default. You are protected from phantom. You're not protected from phantom and repeatable reads. And the other one is a read and committed. All of them could happen. You could end up with phantom reads, non-repeatable reads, and dirty reads. Okay, depending on what you can tolerate, you can set the isolation level. So, for example, as I explained last time, for reporting, if you are doing some reporting, maybe you can tolerate read and committed, because reports, some reports, by the time you generate them, they are already out of date. So why should we wait for other transactions to read the log? We just read, even dirty reads, it's fine. I gave you the example of, let's say, the daily sales of Carrefour as an example, report. If I'm doing it during the day. So it doesn't matter. Once I generate it, it's already out of date because the transactions are always coming in. So no need to really honor this lock-in or shared lock-in. You take, for the purpose of speed, to get that report very quickly and not wait for the records to be unlocked, you just go ahead and set the isolation level to read and committed. Yeah. Now for serializable, let's say you want to as I gave the example of salary increase. Salary increase, you just say, okay, I want to just go ahead, take all my employees, give them 10% increase. This is my salary, as the total salaries that are paid per month. And after I do the change, I'm supposed to have the total salaries times 1.1. Yes? But while doing this operation, if some new employee come in, I don't want them to get 10% increase. You see here, this is what I mean by the phantom reads. Phantom reads is that initially when I read the employees list to give them the 10%, this new employee did not appear. And then suddenly, while I'm doing it, somebody managed to insert a new employee. When I read again, that new employee will appear. If I don't want this scenario to happen, then I raise the isolation level to serializable, and that phantom new record will not appear in my list when I read again. You get the idea. So let me go through this a little bit in more details, just a little bit more. So read and committed, we don't care about any locks. We just tell the database, give us all the data, no matter whether it's locked or unlocked. We tolerate dirty reads. So you can set the isolation level to this. So in here, you are sacrificing consistency in the favor of high concurrency and better speed. And it's mainly useful for reporting, but you take the risk, of course. Okay. So in here, what read and committed. So if with read and committed, dirty read might appear, of course. So here is my, here is my transaction. Transaction 1 updated the salaries of the salary of this employee. Transaction 2 comes along and reads it. This change will be picked up by this query. Even if this one aborts, if T1 aborts, of course, this will end up with dirty read. So this, if the transaction isolation level is set to read and committed, this can happen. This problem can happen. But if I set the isolation level to read committed, this will not happen. Why will not happen? Because T2 will wait. Thank you. Because it will say, oh, this one it's updating, so it must have an exclusive lock. So I'll wait until it's finished, then I run my query. But in here, it will give you the result immediately, but you will end up with a dirty read if T1 changed its mind and rolled back. Okay. Read committed, you are protected from reading uncommitted data. You will never end up with dirty reads. But you are not protected from, it doesn't give you non-repeatable, it doesn't give you repeatable reads. So if you read some data at the beginning of the transaction, did some extra work, came along and read again, you might get different results. So read committed will not protect you from, it does not give you a repeatable read. You might end up with a different result each time. So here is an example. Here is T1. So T1 here, yes, here is T1. I went ahead and read at the beginning of the transaction, give me the details of employee 1, 2, 3. And then I went ahead and did some other work. In the meantime, another transaction came along and updated that particular record I have read. If I read again, I'll pick up this change. So I'm not I'm not getting a repeatable read. Yeah. So the repeatable read protects you from dirty reads, but it does not give you a repeatable read. If you repeat a reading, you might get a different results. Okay. That is the idea. Okay, repeatable read. Repeatable read, as the name suggests, if I set the isolation level to repeatable read, if I run this query, do some other work, and run it again, I will get exact same result. Except if somebody comes along and inserts a new record, that new record will be picked up. This is what I mean by phantom reads. So repeatable read protects you from dirty reads, gives you the ability to have a repeatable read, but it does not protect you from phantom reads. What I mean by phantom read? Some new insert comes along between the first read and the second read. If some new record comes and it matches your workflows, it will appear in the second read. Yeah? So if you want to be protected from phantom reads, what you need to do? Set the isolation level to serializable. If you set the isolation level to serializable, what will happen? You are protected from all anomalies. You cannot get dirty reads. You can repeat your query, or you can repeat your reads and always get the same results. And not only this, you will never pick up some new records that were inserted. In fact, nobody can insert, by the way. That's how it works. Because for serializable, you are locking even the index and locking maybe the whole Sometimes you might even upgrade the lock to the whole table or a range of values. So nobody can insert. They have to wait for you to finish. So that is the idea. So let me summarize this. So read and committed, all these anomalies are possible. With a read committed, all of them possible except dirty reads. You are protected against dirty read. Repeatable read, you are protected against dirty read and non-repeatable read, but phantom read is possible. Serializable, you are protected from all of them. Okay, how this is achieved? Serializable obtains all locks first. So at the beginning, it acquires exclusive locks on the data that it's trying to read. Even for reading, it acquires exclusive lock. Plus, it locks the index. So nobody will be able to insert into that particular range this read transaction is doing. Plus, it uses strict two-phase locking. What does that mean? The locks, the transaction holds on the locks until commit, until the end of the transaction. Yes? Now, repeatable read, it does all of the above, except it does not lock the index. Because it does not lock index, it's allowing inserts to take place. Read committed, it does all the above, but shared locks are released immediately. Shared locks are released immediately. For read and committed, it basically doesn't honor any locks. It doesn't care. It accepts anything, including dirty reads. So you can see here, this is just to highlight that isolation is not an on-off option in a database. It is more a dial that you can kind of customize to your liking, based on what you want to be protected against. You have serializable, repeatable read, read committed, and read uncommitted. 4 standard levels. Those are standard levels. Most databases have this built-in support for these isolation levels. Yes, please.
You mean by, for example, read committed, same as above? You mean serializable or repeated?
Okay.
Same as above.
Same as above, it does all of these.
I mean,
So for example, repeatable reads obtain the locks first, or obtains all locks first. It does strict two-phase locking, but it does not lock the index.
I mean for the read committed, same as above. You mean same as serializable or same like repeated?
Repeated.
Same
Yes, same as the repeated.
above
Repeated.
it.
Yes, above it directly. Yes, yes.
So the best one is serializable here?
In terms of protection, there is no kind of best one. It depends on your requirements. How
It doesn't have the issues that appears in the
yes, it does not have, but it reduces your concurrency. Sorry, can you?
performance will be locked.
The concurrency and performance in the sense of the response time of queries will be higher because other transactions are waiting. Yeah. So because this guy, it locks more, it locks upfront everything it needs, and it doesn't. It holds on the locks. What does that mean? Other transactions need to wait, which means the response time will be higher and the throughput will be lower. Throughput means the number of transactions the database processes per unit of time will be lower. So there is a trade-off, as you can see. There is a trade-off between concurrency and protection against anomalies. Yes, please.
So all of this standard across all the database servers?
Sorry, can you say?
All of this standard across all databases?
Yes, these are standards, part of SQL standard. Or part, yes, I think part of SQL standard, but definitely standardized. Those are standardized. Most are.
But does database provide more levels?
Usually those are the standard levels. There is one more level that is covered by the multi-version concurrency control. It's called snapshot isolation. Snapshot isolation. Those are, to my knowledge, those are the levels available, plus this snapshot isolation. I didn't add here because it is part of another family of concurrency control mechanisms, which is optimistic. Remember, all of those are pessimistic. Pessimistic means they are preventing the anomalies in the first place. They are preventing the conflicts in the first place. They don't allow the conflicts to take place. While optimistic, they assume the conflicts are so rare, we don't need to waste our resources and time on locking. We just let the transactions do their work, and then later we detect if there's a conflict. If there's a conflict, we roll back. So it's a different kind of mental model, or a different way of looking at it. And that part is, you can, for example, in a SQL server, you can set the isolation level snapshot. When you say set isolation level snapshot, the database, instead of using lock-in mechanism, it will use multi-version concurrency control mechanism. I will explain next. Is clear? Yes? Okay, so let me, this one will not take long. I will just finish it, then we'll take the break. Yes, okay? Or should we take the break? Take the break. Okay, that's it. Take the break. So welcome back. So I want now to focus on optimistic concurrency control. This type of concurrency control mechanisms do not use locking. So here the assumption is that the conflicts are the exception, not the rule. They assume that the conflicts are rare. So what we can do, we can just let the transaction do their changes, and before they commit, we verify if there is a conflict. If there's a conflict, then we roll back the transaction. That is the idea of this. I think that the best way to understand it is through an example that I will be explaining shortly. But first what happened is, in this optimistic concurrency control, typically it has 3 phases: phase 1, 2, and 3. In the first phase of the transaction, each transaction has its own private workspace. So the transaction has its own work area, let's say, and this work area, whenever the transaction reads something, it puts it in that work area and then start changing it. And those changes, as you can see here, they are not visible to other transactions because every transaction has its own private space. And then when the transaction is ready, it says, I did all my changes in my own little world, in my own version. Then just before it commits, we go through a validation phase. In validation phase, we check if there is any conflict, if the changes that the transaction has done conflicting with changes that other concurrently running transaction also have done. If there is a conflict, then we will say to this transaction, sorry, we cannot accept your changes. You have to abort. You have to roll back the changes. And since these changes are done in a separate copy, there is no impact whatsoever on our database. We just throw away those changes. And only the changes that have no conflict, they make their way to the global database, or to the database that is visible to everyone. That's the idea of this. So let me explain this in more details through an example. So here is the 3 phases: the modify phase, the validation phase, and then the commit phase. So in the modify phase, as you can see here, I have 2 simple transactions. Transaction 1 read A. At the time of reading, the value of A was 5. And then it went ahead and changed the value of A to 15, and then it wants to commit. All these changes, where these changes are happening? In the private space, in the private workspace of T1. Meantime, at the same time, what happened to T2? T2 did the same. It read A at the time of reading. The A value was 5. It went ahead and changed the value from 5 to 25 and wrote the change. But those changes that we're talking about here, where are done? Where are done in their private workspace. So these changes are not visible in our database yet. At certain stage, one of these transactions will say, I am ready to commit. Can you please go ahead and do the verification to make sure there is no conflict? So we move now to the verification stage. In the verification stage, we ask ourselves, did any other transaction committed some change to A while T2 was running? No. That's basically the question we need to ask ourselves. Did any other concurrently running transaction committed already some changes that affected A? And the way we answer this, the way the database answers this, for each transaction, the database maintains a read set and a write set. In the read set, the database maintains all the items the database has read. And in the write set, the database maintains all the items the transaction has changed. And for each transaction, you can see here in this scenario, the read set up to the time T2 wants to commit, the read set has only A. The write set, there is nothing in the write set because this database, this transaction did not commit or made any change to A yet. And so we have a read set for T1 and we have a read set for T2. We have a write set for T1 and we have a write set for T2. Okay, so the validation, all the validation does, we take the write set of T2 and intersect it with the write set of T1. Basically, the changes that T1 did, we try to see if T1 did changes to the same data item. If this intersection between these two write sets is empty, and also we intersect the read set of T2 intersect it with the write set of T1. If this intersection is empty, then the transaction can go ahead and commit. If this intersection is not empty, then the transaction must abort. So in another way to say it is, we ask ourselves, did any other transaction commit any changes to A while T1 was running? We can see here it's no change, no committed change has been done to A since T2 started. But more precisely, how the algorithm works, database maintains this write set and read set for each transaction. And just before we commit, we do this simple operation. We intersect the write set of T2. In reality, we intersect the write set of T2 with the write set of all concurrent transactions that were committed. And we intersect the read set of T2 with all the write set of concurrent transactions. If the intersection gives us an empty set, then there is no conflict and we can go ahead and commit. When I say go ahead and commit, this value here will become the global value. This will be now visible in our common database. Yeah? Okay, so if we take another example, take a look at this example. Now what we have here, T1 now is ready to commit. T1 is ready to commit. Say before we allow it to commit, we do our validation step. So in our validation step, what we do is we take the write set of T1 and intersect it with the write set of T2. And guess what? This intersection is not empty. these two sets have A in common. So it's not empty, which means T1 cannot commit. Because since T1 have read A, some other concurrently running transaction that's already committed has changed A. So if we go ahead and allow this change, what will happen? What type of anomaly?
Update,
No.
lost update.
Lost update. This is not a dirty read. Because here, if we allow T1 to proceed, what will happen to update T2 did? It will be overwritten, and we will lose that change. Yeah. So that is how it is done. To summarize, in a multi-version concurrency control, each transaction will have its own working space. Each transaction will go ahead and read and write whatever it needs to read and write. And database system is tracking all the items that the transaction have read and all the items the transaction has written. And just before it commits, we go ahead and do verification, validation. So what this validation is, we take the right set of the transaction, and we intersect it with the right set of other concurrently running transactions. If that intersection is not empty, we cannot accept that. We have to abort that particular transaction. We also take the read set of the transaction that wants to commit. We intersect it with the right set of other transaction. If this intersection is not empty, it means the transaction must abort. In another way to say it, if you recall, if we have a write to the same item, this will cause a conflict. So this is not allowed. Sorry. A write is not allowed. If we have a read write, of course this is also not allowed. And if we have a read is okay. If we have a write read, also not allowed. No, but in this scenario, because we always compare, here is the condition. Take a look at the condition for a transaction to be able to commit its changes. What we need to do, we take the right set of the transaction that wants to commit, we intersect it with the right set of transactions that's committed while Ti was running. Okay, and we take the read set. You see here, we take the read set of Ti and we intersect it with the right set of concurrently running transaction that's already committed. If these two intersection gives us are empty, then the transaction is allowed to go ahead, which means there is no conflict that will be produced. Otherwise, if any of this intersection is not empty, the transaction must abort. That's the idea of this optimistic concurrency control. Database, each transaction has its own version, its own world, its own working space. It does whatever it needs to do in that private space. When it's time to commit, we check if this current transaction that we want to commit, does it conflict with other concurrently running transaction that's already committed? Is there any conflict? Did somebody write to the items that we already read? Or did somebody write to the items that we also intending to write? If this scenario, if there is a conflict, somebody modified what we read, or somebody modified what we intending to write, this will cause a conflict, which means our transaction must abort. It cannot go ahead and proceed. That's the idea. If it's abort, we just take the copies, this kind of workspace of the transaction, and we just throw it away. Of course, there's a loss of effort and loss of time spent on the transaction. We just throw it away. But this is affordable because this type of systems assume that the conflicts are rare. It assumes that transactions kind of working on different parts of the database only occasionally they kind of clash and conflict. So if this is the case, if the contention is low, if transactions are not competing with each other too much, then this will work very, very well. Otherwise, this is too much overhead compared to locking. So for example, if this is, let's say this is a sales system, and each salesperson is dealing with different customers, then this will work quite well because every salesperson will be dealing with their own customers, changing their own customers. They will not change each other. Very rare they will change each other at the same time. So each transaction is accessing different part of the database. Then in this case, this will work very well. So to summarize, so here it is. So what I have here is the optimistic concurrency control works well when the number of conflicts is low and transactions are accessing disjoint subset of the data. And basically because of this fact, the probability of conflict is low. And because the probability of conflict is low, there is no need to every time lock before we acquire reading or writing. But the problem, of course, in here, the overhead is much higher compared to the locking, because each transaction must have its own space. Whenever it reads or writes, it must copy the data to its own space, make the changes. Also, the validation is quite heavy. The database must maintain for each transaction the write set and the read set, and the validation need to intersect those write set with the write set of other concurrently running transaction, and the read set of the transaction that we want to commit with the write set of other concurrently running transaction. So the validation is quite heavy. And after all of this, if a conflict arises, after all this effort, we just throw the whole effort away if a conflict arises. So if there is a lot of contention and a lot of transactions are stepping on each other's area, then this will perform very poorly. But if there is the case of disjoint subset and transactions are accessing different subset of the database, then this will work very well compared to locking.
Which transaction? The one that is already committed?
No, already committed, it won't be touched. It's abort the transaction that is trying to commit. So look, the way it works is like this. Each transaction has its own space, and it works as it pleases. It does all the changes, reading, writing, all these changes, but it's in its own workspace. When the transaction is ready to commit, it says to the transaction manager, please, I'm ready to commit. Transaction manager says, come here, give me your write sets, give me your read sets, and it goes and does the validation. If it finds there is a conflict, it will communicate the bad news to the transaction. Abort yourself. I will not accept the changes that you have done. So it's the transaction that wants to commit. It will go through the validation stage, and this validation will be changes of the transaction that want to commit against the changes of the transactions already committed while the transaction was running. Not all the ones that committed last week or 1 year ago, whatever. The ones that were committed while the transaction concurrently. They were running, the other transactions were running concurrently, but they had the chance to finish and commit. We check the conflict with those transactions that already committed. Those are committed. We cannot undo them or abort them. Halas, they made their way, and they are now they are visible in the common database. We cannot abort them. We abort the one that asked us to say, oh, I am ready to commit. We don't just say, oh, come along, welcome, let's do whatever you asked us to do. We go through the validation phase. The validation phase will either have go ahead, commit, or rollback. Go ahead and commit means take the changes done in the private space and reflect it in the global or common database. It's clear? That's why we call it a multi-version concurrency control. So at one particular stage, you might have multiple versions in different private spaces. But some of them will win, some of them have to abort if they will end up causing us a conflict.